We are on the threshold of what may be the most significant leap in the history of computing: the transition from transistor-based processing to the manipulation of atoms themselves. This third stage in the evolution of computers is embodied in quantum computing, a paradigm that represents not just an increase in power, but a fundamentally different relationship with the physical world. The emergence of quantum computers, especially when integrated with artificial intelligence, AI, is not just a technological breakthrough, but potentially a transformation of reality itself. Quantum computers don't just speed up computing. They fundamentally change how information is stored, processed, and understood. Google's presentation of its Willow chip, a 105-qubit quantum processor, is a striking example of this. In less than 5 minutes, this chip performed calculations that would take the world's fastest classical supercomputers more than 10 to the 25th years to complete, longer than the known age of the universe. The implications of such power go far beyond faster computing. AI integrated with quantum computing doesn't just model the laws of physics, it could start rewriting them. This potential to manipulate matter, not just in a metaphorical or virtual sense, but physically, is causing both speculation and serious concern. Physicist Michio Kaku has sounded the alarm. Once quantum AI begins to manipulate fundamental properties of matter such as mass, we will enter a realm where traditional laws of physics and reality itself may cease to apply. When we talk about changing mass, we don't mean traditional weight or volume. We're talking about changing resistance to acceleration, the thing that gives an object inertia. Mass isn't just a number, it's a defining property of how matter behaves in the universe. What if that could change? Some materials already point to this possibility. At the University of Pennsylvania, scientists have created metamaterials in which electrons behave as if they have zero mass. They move freely in certain directions. Elsewhere, quantum liquids have demonstrated negative effective mass, acceleration in the opposite direction to the applied force. This is not speculation. These phenomena have been observed and measured. Now imagine that AI not only models such behavior, but also creates new materials from scratch, materials with programmable mass properties. This is where Google's quantum AI becomes not just a tool, but a potential architect of reality. Let's look at 5 hypothetical but scientifically plausible ways in which AI-based quantum systems could manipulate mass. 1. Tuning the Higgs interaction. All matter gets its mass from interacting with the Higgs field. If quantum AI figures out how to locally tune this interaction, even slightly, it could effectively allow particles to behave as if they became heavier, lighter, or massless. This would be like turning a knob on the very structure of identity in physical space. 2. Vacuum engineering. The vacuum in space is not empty. It is filled with virtual particles and hidden energy. The Casimir effect already shows how energy density can vary between objects in a vacuum. If AI can precisely manipulate this energy density, it can change the behavior of particles in these areas, effectively changing inertial properties without changing the particles themselves. 3. AI-designed metamaterials. This is already in development. Quantum AI can design materials with exotic properties, structures in which particles behave as if their mass is close to zero or even negative. This means that AI will soon be able to create environments in which particle mass is an engineering parameter rather than a constant. 4. Frameshift simulation. Einstein's theory of relativity shows us that massive rotating objects move space-time around themselves, an effect known as frameshift. If AI can artificially simulate and reproduce this effect under controlled conditions, it will be able to model mass or inertia in new ways, potentially changing how objects move through space. 5. Creating lattice-calibrated particles. By simulating lattice-calibrated theories, AI could discover previously unknown quantum particles or states of matter with tunable mass. These would not be fictional constructs, but real objects of experimental physics that would open up entirely new ways of manipulating matter. Quantum computing outperforms classical computers in modeling systems that the latter cannot reproduce. Google's Willow chip is not just faster, it processes fundamental interactions between particles in entirely new ways. These simulations are no longer academic exercises. They are beginning to influence real experimental developments. Consider the following examples. Metamaterials developed in laboratories now allow electrons to move in one direction as if they have no mass. Bose-Einstein condensates, quantum liquids cooled to near absolute zero, exhibit negative effective mass. Experiments with the Casimir effect demonstrate the possibility of manipulating vacuum energy. Now add to that the optimization and learning capabilities of AI. Once quantum AI begins to design experiments, discover patterns, and create real materials based on quantum simulations, we will be closer to the threshold where theoretical designs become technological applications. If AI discovers a new configuration of the vacuum, or a new way to influence the interaction of particles with fundamental fields such as the Higgs field, the result could be not just a new material, but a change in how we define and use mass. Michio Kaku, one of the most respected authorities in theoretical physics, has emphasized that the convergence of AI and quantum computing marks a historic revolution. But with this comes a serious warning. Once machines start making their own decisions, especially in areas we barely understand, can we really maintain control? The danger lies not only in creating smarter AI, it lies in creating AI that can change the structure of the universe, alter resistance, motion, and even time, and do so using methods that humans may not fully understand or predict. If AI learns to change inertial resistance or simulate the curvature of space-time, it will ultimately be able to manipulate gravity, time dilation, material resistance, and thermodynamic properties. We are no longer just writing software. We may be creating systems that will redefine the physical constants that have governed the universe for 13.8 billion years. If quantum AI cracks the code of mass manipulation, even on a small scale, the consequences will be almost unimaginable. Spacecraft will be able to change their mass to achieve near-instantaneous acceleration. Thanks to customizable inertia, propulsion systems will no longer be limited by the laws of Newtonian mechanics. Travel to distant planets and even interstellar flight will become possible. Imagine drones that lose mass in flight and become invisible to radar. Projectiles that lose mass to fly farther and then regain it upon impact. Materials that deform under the influence of energy, absorbing shocks or radiation without resistance. Traditional weapons and defenses will become obsolete overnight. Whoever masters this technology first will gain unparalleled power. Mass affects gravity, and gravity affects time. The ability to regulate local mass conditions could make it possible to alter the perception of time or its passage, opening the door to science fiction-like technologies, or time manipulation. Mass control technologies could catalyze a geopolitical arms race. Countries will compete to create weapons or defenses against invisible systems that violate the laws of physics. Kaku warns that this is not just a new tool, it is the next level of escalation, comparable to nuclear weapons. One of the most disturbing developments is the growing convergence of simulation and reality. Quantum AI is beginning to model quantum fields and the behavior of matter so accurately that simulations are leading to the creation of real materials. These are not crude prototypes. These are functional, programmable materials that exhibit behavior once thought impossible. Quantum AI can simulate interactions in the Higgs field, simulate the behavior of new particles, test hypothetical vacuums and energy states, and unlike human researchers, AI is not limited by the known laws of physics. It explores all possibilities, including those we reject or overlook. This means that AI could eventually stumble upon a configuration that alters reality too much, manipulating fields in ways we didn't expect, or worse, can't contain. The ability to manipulate mass is no longer theoretical. It is experimental and may soon become programmable. As quantum AI advances, we must ask ourselves a pressing question: can we control what we create? This is not just a matter of scientific responsibility. It is a matter of substantial risk. Could altered vacuum states lead to the collapse of the universe, as some physicists suggest? Could uncontrolled quantum modeling destabilize natural forces? Could mass manipulation, even on a small scale, lead to unforeseen consequences that we cannot reverse? It is no longer enough to ask whether something is possible. We must now ask whether it is reasonable and how we can ensure that ethical standards are upheld in this area. To understand what is at stake, we must return to the basics. Rest mass is an intrinsic property of a particle that is unchangeable under normal conditions. Effective mass describes the behavior of particles in certain materials or environments. The Higgs field gives particles their rest mass. Interaction with this field determines resistance to motion, inertia. Einstein showed us that mass and energy are interchangeable. E equals mc squared. Nuclear reactions demonstrate this every day. For example, the sun converts hydrogen into energy while losing mass. A new phenomenon is effective mass engineering. The Casimir effect manipulates the energy of the vacuum. Bose-Einstein condensates demonstrate negative mass. Metamaterials cause electrons to behave as if they have no mass. None of this changes fundamental rest mass, but it simulates changes in mass. And that may be enough to rethink what we consider real. So, has Google's quantum AI changed mass? Not in a literal, fundamental sense, but it has brought us to the brink, to modeling, designing, and predicting conditions in which effective mass behaves as it does in science fiction. It's not about pressing a button. It's about quantum AI opening up blueprints of reality, patterns that allow us to manipulate the world in ways that classical science couldn't foresee. We are entering a world where the very fabric of reality becomes a space for design, where the laws of motion, inertia, and perhaps even time are variables. The systems we are creating now, Google's Willow chip, metamaterials, quantum liquids, are just the beginning. The fusion of artificial intelligence and quantum energy could make nothing in the universe unattainable. Michio Kaku's warning is not just about power. It is about the responsibility for the ethical, wise, and collaborative use of that power. If we are not careful, what we discover in this new paradigm may exceed our ability to control it. But if we are careful, then perhaps we are on the verge of reimagining reality.